I want to point out that the last integral we looked at can be rewritten in this form very simply. So if I take out the factor of a half, I can write this as cos of x squared times the derivative of x squared. In other words, I've written this in a standard form where out front I have a derivative of the new variable and then I have a function of the new variable. So here I can associate u specifically with x squared, and f is the function cos, and du by dx is 2x. Hopefully you can see the mapping here. And any integral of this form I can do straight away because all I need to do is replace the measure of integration here, remembering that du is equal to du dx dx. And you can see that this form has both a dx and a du by dx, so I've got this, so I can rewrite this as the integral of f of u du. And now this is no longer referring to x, it's entirely in terms of a new variable, and provided I can integrate f, which in this case I could, then I can get the result simply. So watch out for integrals which can be rearranged into this kind of form. In a moment we'll look at a special example which is very, very useful. Let's try another simple example. In this case we're going to integrate x over 1 plus x squared dx. And in this case the best substitution to make is to replace the denominator here with the new variable. So I'm going to say let u equal 1 plus x squared. So then we have du is equal to 2x dx, remembering that du is equal to du dx dx, and in this case du dx is 2x from there. Okay, and all I need to do is put that into here. Dx will be equal to du over 2x, so I'll get, altogether bringing out the half, an integral of du over u, once I've made the cancellation here and here. Okay, so this can be integrated very quickly. This is the integral of 1 over u, which will be log u. So here we are, half log u. And here I've put in the absolute value signs from the earlier video clip. Finally, we put back in the original variable. So it's a half log 1 plus x squared plus a constant. Easy, simple and straightforward. But before going on, I should note that this worked because this integrand here is a special case of the general rule which we saw in the previous clip. In fact, it's a special case which comes up all the time when we have an integral which can be written as some amount of du by dx over u dx. Then that always comes out as log of u. And in this case, the u was the denominator, the du by dx, well that was the 2x, okay, and I needed to bring out a factor of half to make all of that work. But you can see that whenever we can recognize that our integrand is du by dx divided by u, where u is any new variable, then we can integrate straight away to get log u. Okay. So I hope that's clear. Now I'm going to look at two examples of integrals which look superficially very similar, but which require different methods. So the first integral is that of 1 over 1 plus x squared. The second integral is that of 1 over 1 minus x squared. So all that's different is a sign here. The first we're going to do with a substitution, whereas the second we're going to do using a method of partial fractions. So we'll see how both work. You've already seen substitution. The key thing in substitution is to choose the right substitution. Here, without experience, you might not guess that letting x equals tan u is the right thing to do here. But let's see how that works. Well, this method is going to rely on the trigonometric identity, which is fairly fundamental. Sine squared plus cos squared equals 1. Now, if I were to divide this through by cos squared, then I reach tan squared plus 1 equals 1 over cos squared. 1 over cos squared is the same thing as sec squared. So here's another version of the trigonometric identity. And now you can see this is the motivation for making the substitution, because here I've got 1 plus x squared, and that's what features here. So I can replace 1 plus x squared with sec squared u. And as before, we also need to replace the measure of integration, and dx will be equal to dx by du, and the derivative of tan u is also sec squared u. So that's how this method is going to work. We can replace the denominator with sec squared u, and in replacing the measure we also have a sec squared u. They will cancel out, and so simply I will be the integral of du after this cancellation has occurred. So therefore u plus c, and now finally we put back in here, so that leads us to inverse tan x plus c. Okay, so that worked. It seemed like a bit of a trick, and I guess it is. But in fact, there's a few standard forms for integrals which have standard substitutions. And I don't have time to go through them all, but now's the time to check your notes and look at the standard integrals which you can do with standard substitutions, because there's actually not as many as you might think. Now moving on to the right-hand side, we have the same looking integrand, but this time with a minus sign. And this time we can proceed in a different fashion because the denominator can be factorized. So I can factorize that as 1 minus x times 1 plus x. Just check that for yourselves. When we multiply this out, the cross terms will cancel and we're left with a 1 minus x squared. So the next step here is to try to split this up so that I've got something over 1 minus x plus something over 1 plus x. And I can write straight away, well I'll go through it properly next time, that this is the same as 1 over 1 plus x plus 1 over 1 minus x. Well, when I multiply this out, in other words, if I multiply this by 1 minus x on top and bottom, and this by 1 plus x on top and bottom, then I get the same denominator, and on the top I'd have 1 minus x plus 1 plus x. So the x's will cancel, I'd be left with a 2 on top, and that's why I put the half in here. Don't worry about those steps, we'll do it again next time. Now, each of these I can integrate straight away. They integrate into logs. So I have a half log of 1 plus x, and then a minus log of 1 minus x. And that minus will come from the fact that we have a minus in front of the x here. If you don't believe me, check that with the substitution. And finally, I should put it the constant. Finally, provided that x is less than 1, I can rewrite this as 1 plus x over 1 minus x in the argument. So there we have two apparently similar integrands, but two quite different methods and two results which look dissimilar. But actually, this is related to tanh, the hyperbolic function. I don't have time to go into that now, but this can be rewritten in terms of inverse tanh, which would then makes it look formally more like this side.